Right then, welcome back. Today we're going to do is not the right word. I'm going to discuss and review a very powerful result in quantum field theory concerning the renormalizability of 5-4 theory. Now what I tell you today will be also applicable to other renormalizable quantum fields, but well, the work increases as you consider more and more complicated quantum fields. So there's no way I will be able to prove this result to you today. It's an extraordinarily complicated theorem of Bogoliubov, Karasiuk, Hep, and Zimmermann, otherwise known as the BPHZ theorem. And it involves a very intricate amount of combinatorics to actually prove the renormalizability of 5-4 theory. So by renormalizability, remember what this means is that what does renormalizability mean? It means that you have a bunch of cutoff field theories, or bunch of cutoff theories, determined by a finite number of parameters, and so in the last lecture I denoted these parameters by Z, and the whole theory depends also on a cutoff So renormalizability means you have a bunch of cutoff theories determined by a finite number of pre-parameters, here they are, such that for all observations or all observable quantities, which of course are determined by Hermitian or self-adjoint operators, these expectation values here, which depend on these free parameters and on the cutoff lambda, can be made to not depend on this cutoff. Let's call this A alpha. So these numbers here are all observable, so they're in principle determined by an experiment. And a renormalizability implies that it's possible to fix these values to equal their experimentally determined values, which are fixed, they can't change. The mass of the electron is the mass of the electron, and so on, by allowing these parameters to depend on lambda. Oops. That's what renormalizability means. It means given a finite list of numbers, you can match all experimentally determinable quantities, so these are operationally defined quantities, by redefining these parameters for, as you change lambda, as you choose different cutoffs lambda. Now that should cause you no distress if you don't think of these quantities as being directly measurable. If you think of these quantities as being, as corresponding to some kind of element of reality, then of course you have to worry about what does this all mean, especially if the z's can go to infinity. Right. But for us, we're living in the world of effective field theory, which means that we don't interpret these things as being elements of reality. This is just a list of effective theories to determine the physics. Right, that's what renormalizability means. Oh, okay, there's a slightly weakened form. This is the one that actually applies in the examples we're going to cover. The weak form of renormalizability is that by redefining we don't quite get that we can match all these values to the experimentally determined quantities. We only get that up to quantities that vanish. So actually what happens in practice is you don't quite get that you can match all the experimentally determined quantities exactly for all lambda, only up to corrections that decay as this cutoff is taken to infinity. That's the best you can get from an actual quantum field theory such as phi-4 theory, what we're going to discuss today. So that's almost as good, right? It does, there will be some quantities that depend on the cutoff. There's actually no way out of this. But they depend on the cutoff in such a fashion that if you raise the cutoff, if you chose a bigger one, then the dependence is smaller. So you can get rid of the dependence by just taking the cutoff as large as you like. So I'm going to discuss this aspect first, and then I will give a brief sort of overview of how to implement the renormalizability theorem in practice of B, P, H, and Z. And then that'll be it, I think, for perturbative quantum field theory and renormalizability. And then in the next lecture, we'll start gauge theories. But for now, let's see if we can at least argue to you some of these features here for the case of phi-4 theory. So phi-4 theory is determined by a Hamiltonian that depends on three parameters: an m parameter, a lambda parameter, and actually something else called a z parameter, which I'll introduce to you presently. Field strength renormalization. We don't need to worry about that though at the moment. And of course, our theories are indexed by a cutoff as well. And here's the big question. Here's the big question. Is phi-4 theory so defined as a bunch of theories that depend on three parameters and a cutoff renormalizable in the sense here that I've... Now, that's an amazing result if possible, because What that would mean is that you can fit an infinite number of quantities by adjusting just 3 quantities. So it's a highly overdetermined set of equations, this renormalizability condition. So you're totally entitled to believe that this could never happen. This is never possible. Of course, there are some data points where you know it is possible. So for example, when lambda is 0 and z is 1, then you actually know the answer. It's just standard free field theory, and that is actually renormalizable. It doesn't depend on the cutoff. It gives finite quantities for observable, finite answers for observable quantities. So there are actually data points that are actually renormalizable theories that you know already, free theories. The challenge is, can we find an interacting theory with our tools of perturbation theory that could be argued to be renormalizable? So we don't actually quite, to be clear, we don't actually achieve this goal. So we don't even achieve this actually with the BPHZ theorem, because all of the arguments I'm going to make will be perturbative in nature. So you have to worry that even though you'll be able to make the perturbation series for these quantities not depend on lambda or the cutoff, that doesn't mean that the theory doesn't depend on the cutoff. That just means that using the tool of perturbation theory, it looks as though everything doesn't depend on the cutoff. But we're still stuck with perturbation theory as our calculational tool. So you have to, the very hard problem that's only been solved in 1+1 dimensions for very small values of lambda is to determine, or kc, sorry, is to determine whether or not this theory gives cutoff independent predictions. That's only been done in this low dimensional case. All the other high dimensional cases hasn't been done. Only at the level of perturbation theory. But that's so strong and it matches the experiment so well that I think you'd have to be pretty combative to argue that field theories aren't renormalized, that phi-4 theory is not renormalizable outside of perturbation theory. All right. So is phi-4 theory renormalizable? Can we adjust these 3 free parameters here to absorb all dependence on the cutoff, or at least make it go away to the level where it decays with lambda? Okay, the answer is astonishingly yes. And to describe how this result actually is rather compelling, so I'm gonna first derive an auxiliary result that will show us that only a few quantities will ever depend on the cutoff anyway. So this is already kind of amazing. So to describe this result, I'm going to talk about a concept called the degree of divergence of a diagram. So consider a Feynman diagram. So what is that? It's just an integral, remember? Feynman diagrams are integrals. With BE external lines. All right, here's a definition. We noticed last lecture that some diagrams diverge. So if you put a cutoff in momentum of value kc, then as the momentum cutoff is removed, the integral corresponding to the diagram gets bigger and bigger and bigger as the cutoff is taken away. Bad, right? And the diagram that we encountered in the last lecture, which had that property, was this double cross thingy, that diagram there. This one diverges, as you proved in the exercises, as logarithm of the cutoff. So we say that such a diagram diverging like that has superficial degree of divergence d equals naught. So if the diagram is diverging as a logarithm in the cutoff, we say it has superficial degree of divergence 0. And if it diverges as worse as kc to the power d, then we say that it has superficial degree of divergence d. So d could be a non-integer or an integer. It's usually an integer. So the superficial degree of divergence measures the badness of a diagram as you take the cutoff larger and larger and larger. Some diagrams are good, some are bad. And we're going to I'm going to now quote to you a theorem in quote marks, in scare quotes, to indicate that I'm not really going to prove this at the level of rigor sufficient for mathematics, but we're going to argue this result, and you'll be able to make it more rigorous if you work sufficiently hard. It turns out that the superficial degree of divergence of a diagram is equal to 4, which is actually the space-time dimension, minus BE. Okay, that's pretty amazing. Let's do some examples to get a feel for why this is pretty amazing before we get into the proof or proof argument. So consider a diagram which has two external legs. So number of external legs equals 2. So the claim is this diagram diverges as kc to the power 2, right? That's what the theorem says. So now let's look at the propagator. So if you look at the propagator, we have to integrate over all the momenta, the propagator, just a simple line, then this indeed scales as kc squared. So there's some sense to this example. So we integrate over undetermined momenta, that's why there's an integral. Now this theorem's kind of amazing, right? I mean, okay, in the case of the propagator, you can kind of see that it scales as lambda to the, as kc to the 2. But what this theorem says is no matter what you put inside that shaded bubble, no matter how complicated you make the Feynman diagram within, it'll still diverge as kc squared. That's super astonishing, right? Why should it be that all this super complicated integral with lots of stuff inside should still diverge only as kc squared? So, another example. Here's a possible diagram. Here's a legal diagram that you could have in here. All right. That's a legal Feynman diagram right there, I believe. Oh no, it's not quite a legal Feynman diagram. Now everything's got degree 4? Yeah, nearly. This is going under. There. All right, you can go crazy thinking of things. It has 2 external lines and a whole mess of vertices inside and loops and everything. But the theorem says that this has the same divergence as just the basic propagator. You're entitled to be astonished by that. What about example 2? What's the degree of divergence of this diagram? Well, it has 4 external edges. BE is 4. And D is 0, which means that it has at most a logarithmic divergence in KC. No matter what you put inside. Any diagram with 4 external legs will diverge as log, at most as log of Kc. And finally, and most compellingly, the reason I haven't chosen BE is 3 or 1 is because there are no diagrams with 3 or 1 external edges. Let's go to 6 and above. How do diagrams with 6 external legs scale? Now here's the really amazing result. 4 minus 6 is negative, yeah? It's minus 2. So, according to our theorem, diagrams with 6 external legs scale as 1 over Kc squared. That's pretty amazing. That means that as long as you've got a process involving 6 or more particles, then it doesn't, the predicted value shouldn't really depend on the cutoff, because as you take the cutoff larger, these terms vanish. I mean, there's all kinds of subtleties you have to worry about, summing series and so on. But at a very superficial level, at a naive level, the only diagrams that are ever likely to depend on the cutoff in a way that would be observable, have observable consequences, are the diagrams with 4 external legs or 2 external legs. Everything else is like exempt. Don't have to worry about how they diverge. And I'm going to argue this to you. I mean, the proof is astonishingly simple. I'll do, but before I do that, I'll do a couple more examples just to highlight some notation that we're going to introduce. we're going to need some numbers. One of them is the number of internal lines. The next number we need is the number of vertices. And the third thing we're going to need is the number of loops. So these quantities are defined for any diagram. I'll just give you a question.
Sorry, maybe I missed it, but is this theorem
Is this theorem
the
the BPHZ theorem?
Exactly.
This is not the BPHZ theorem. Okay. Yeah, I didn't say that. This is a intermediate result. I don't know how to call this. Let's call it the degree of divergence theorem.
So
It has no name. The BPHZ theorem says that that phi-4 theory is renormalizable, so that's not that statement there. That's a different statement. This is something that helps you along the way, but it's sort of sufficiently useful as a physical criteria to determine if a theory is renormalizable or not, that it's worth quoting by itself. All right, so we're going to introduce some notations for a diagram: BI, number of internal lines; V, number of vertices; L equals number of loops. And these numbers will all be important in the proof of this theorem. So let's do some further examples. Let's try this one. It's not the one I've written down, but let's see what happens. So VBI is 3 for this diagram. The number of vertices is 2, and the number of loops is 2. Yeah, we've got one loop here and one loop here. Okay, let's do a fourth example. Figure of 8 on top of a line. Number of internal lines equals 1, 2, 3, 4. No, 3. 1, 2, 3. Ah, yeah, because it's a loop. This is a good example here. So we have 2 internal lines, one line here, and a third internal line. So it's the same line. So it's 3 internal lines. We have 2 vertices. And how many loops do we have? Well, we have 2, right? Yep.
In example 3, how do you count the loops? Why didn't you count the one all the way around, but only the ones that go through the middle?
How did I count the loops is the question. So it's the number of undetermined momenta is the number of loops. So there's, every time you've got a situation where you can go around like that, that's a loop. And one more for good measure. This diagram here has 2 loops. Well, let's start with the internal lines. 5 internal lines, 2 loops, 4 vertices, and degree of divergence is -2. The degree of divergence here is 2, and the degree of divergence here is 2. Okay, all these numbers will be important in the way we make the proof of our theorem. Yo, another question.
Is this another example? Because this is example number 3, and then goes on.
Oh, sorry. Oh, I thought I numbered these consecutively. So the question was, is this another example? Yeah, it's another example. Sorry, I numbered it wrong. this should be IV, this should be V, and this should be VI. let's make a proof. Of course, I quoted the theorem with scare quotes, so I can hardly prove a scare quoted theorem without scare quotes. So we're going to do a quote marks proof. Okay. The number of loops Observation 1. The number of loops in a diagram corresponds to the number of undetermined momenta in your diagram, which means that's the number of these integrals you've got to do. And it's really these that make any diagram diverge. Anything else in the Feynman diagram technology doesn't make diagrams divergent. On the contrary, if you didn't have to do loop integrals, you wouldn't have divergent diagrams. So the loop integrals are morally, you know, what does a loop integral do? Well, it's like multiplying by the cutoff to the power 4, isn't it? Because sort of, you can sort of think of it as multiplying it by the cutoff to the power 4. So this is the bad stuff, right? The number of loops, the more loops you have, the worse things are going to be. That much is what this combinatorics is already telling us. Okay. All right. So most naively, looking at a diagram, you'd think there'd be BI integrals like that, right? One for each undetermined momenta. But of course, momentum conservation reduces the number. Right? So you have these undetermined momenta, and then you impose momentum conservation at each vertex. Here, 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 here. So what does that do? So that takes your initial 1, 2, 3, 4, 5 undetermined momenta and reduces that number by 1, 2, 3, 4, so to give us, in fact, somehow I've made a mistake there. Oh yeah, per loop we get an undetermined momenta, so I was counting it twice. So you get when you impose momentum conservation on each vertex, you end up with only an undetermined momentum per loop. We've noticed that already. So L, which is the number of integrals you need to do, is equal to the number of internal lines minus the number of vertices, but minus 1. I'll leave you to ponder that for a moment. Now, another simple observation. Each vertex has 4 lines sticking to it. And each line connects 2 vertices. So we have that 4 times the number of vertices is equal to the number of external lines, right? There's 4 lines per vertex. Now we've got to count all the lines. There's 4 external lines. There's external lines. They only touch a vertex once. They don't touch 2 vertices. They only touch 1 vertex. Plus, all the internal lines, well, they touch 2 vertices, so there's some overcounting here. So you have to put a 2 there. So we have that 4 times V equals BE plus 2BI. And we have that L equals BI minus V minus 1. Now, as before, for each loop there's an integral, and for each line there is a propagator. So propagators are good, loops are bad. Propagators put powers of k on the denominator. Loops put powers of k on the numerator. So the degree of divergence, well, you get, this has degree of divergence 1 over kc, right? This propagator here. And this has sort of degree of divergence kc to the 4. Oh, squared. So the degree of divergence of a diagram is 4 times the number of loops. For each loop, you pick up a power of kc. But, of course, for every internal line, you drop it by a power of 2. So, 2bi. And now we can do the rest. Right? We have done the combinatorics. So the theorem says that the degree of divergence is 4 minus the number of external lines. So we've got to get rid of L, and we've got to get rid of I in favor of external lines. So the next line, well, we know that the number of loops is bi minus v minus 1. And the number of internal lines, we have a formula for that. It's 4 times v minus be. I think I got that correct. No, yeah, right. 2bi equals 4v minus be. Yeah. Okay. What comes now? Oh, yeah. I got to do it again. something went wrong.
Shouldn't the minus 4 have a V on it?
Shouldn't the -4 here?
Multiplying off the left. In the last line.
Oh, yeah, you're right, absolutely. No, wait on.
No.
No.
I meant the -4. -4 with left.
I don't see a -4, I guess is my problem here. -4. Where do you see a -4?
The third, in the last line.
Yes.
Next one. This one.
Yes.
Didn't that come from?
Oh, there's a V.
Yeah.
Ah, thank you. Now things are looking better. Aha. All right. Algebra, right? 8V, 4V, 4V. That cancels. BE. Now the BE's. Oh, no. We got -2BE plus BE. So what do we end with? 4 minus BE. Super. It's an elegant bit of combinatorics, and we've learned an astonishingly general result. So we've learned that the only diagrams that are ever going to cause us problems are ones that make predictions about scattering or about propagation. So the other processes that you can observe in high energy physics, none of those really depend on the cutoff already, if you're willing to believe that a diagram expansion is convergent, which we are for this course. So this result should give you real confidence now that by adjusting a couple of parameters, we might be able to eliminate that last amount of divergence coming from these scattering type processes and from propagation type processes. Now the combinatorics does not work out so nicely if your interaction has a higher degree than 4. So if you have a D equals 5 vertex, so instead of 4 vertices having 4 edges, you have vertices with 5 or 6 or 7, more than the space-time dimension, then things don't work out so nicely. I haven't done that calculation. I'll leave that as an exercise. And so you notice that there is a kind of delicate cancellation that occurs here in this argument, particularly in this last line here. If you had 6V up there, for example, and if you had, well, that result stays the same here. So if you had 6V, what goes wrong? I'll just do a little side computation to see if I can work out what's going to happen. So 6V equals BE plus 2BI. And then the degree of divergence would then be the 4 times the loops minus 2BI, which equals 4L minus 6V minus BE. Yeah. Which is 4 6bi minus v minus 1 minus 6b minus be. And then we should have something go wrong now. Maybe not. I haven't done this, so anything can happen right now.
Sorry, doesn't the number of loops also depend on the number of lines on each vertex?
Oh yeah. Ah yeah, okay, so this yeah, right. Yeah, momentum conservation works differently when you have 6 vertices. Ah, yeah, good point. Okay, so I'll just leave that as an exercise to work out the degree of divergence of a diagram. Actually, I'm not sure. Okay. All right, this is a little exercise for you. Do this with phi n theory. What I'm going to do is give you a very practical way of carrying out this process of shifting coupling constants or parameters to eliminate dependence on the cutoff. Before I do that, I just want to mention something about the word divergence. So we use the word divergence not directly to mean that something goes to infinity. The word divergence is used throughout here to mean that an observable quantity seems to depend on the cutoff. So a diagram is divergent if it leads to a observable quantity depending on the cutoff in an observable way. It's not divergent if it, as the cutoff is removed, leads to a prediction or a quantity that you could observe not depending on the cutoff. So divergence is more about dependence on the cutoff rather than an actual infinity. The infinity is only there if you insist on sending that cutoff to infinity, because you are, you firmly philosophically believe that the cutoff should be infinity because you're dealing with an element of reality. Now, how do we solve the problem, though? I haven't quite solved it yet. By shifting parameters, how do we make sure that no observable quantities depend on the cutoff? Well, you have to shift the parameters. That's sort of obvious, right? So if you look at the Lagrangian for phi-4 theory, then it can depend on 3 parameters, as I said, and I'll put the parameters in now. So there's this additional parameter that you haven't. You have a question?
Do we also call it divergent if it doesn't go to infinity when we send Kc to infinity?
Ooh. Okay. Can I interpret your question as saying, is a diagram divergent if it leads to a quantity that doesn't go to infinity but still depends on the cutoff? Yeah, let's call it divergent because that would lead to a prediction that depends on the cutoff. Though this doesn't happen for phi-4 theory. You either get logs or powers at perturbation theory level. Who knows in the non-perturbative level, but at the perturbative level, that's what you get. All right, so this thing here is called the field strength renormalization. It's an additional parameter that you can have. You know, a Lagrangian can depend on zillions of parameters, but it turns out for phi-4 theory we have 3. Okay, I'm going to write this as L is a function of Z1, Z2, and Z3. Because we really don't want to. We don't want to think of these numbers as being corresponding to real quantities, so I like to just label them as Zs. Zs are somehow more neutral than M. M is just a mass. You want to read it as a mass. Oops. Now, the first step in doing a practical calculation where we're going to shift Z, M, and lambda to remove the dependence of our predictions on the cutoff. That's the whole name of the game. So there's a neat way of doing that called this renormalized perturbation theory. So how it works is you write your Lagrangian as some physical Lagrangian plus things called counter terms. So I'm just going to take exactly that Lagrangian and write it in a different way. And this different way is I think I do want a bracket here, don't I? Yeah. So we have some physical mass now. This is the actual physical mass of the phi field. Z, this field strength parameter, renormalization parameter, that's 1. For the physical Lagrangian. And you've also got some lambda physical. And then, well, that doesn't equal that, does it, right? Because we have to make this equal. There's going to be some differences. So we're going to add on the terms. So this is lambda phys. I'm going to add on terms to correct for the fact that this isn't equal to that. And the terms that are wrong, well, they're these, right? There's this bit that should have come from this field strength renormalization. There's this bit that should have come from the non-physical mass, and there's this bit that should have come from the non-physical parameter corresponding to lambda. Now these those 3 numbers there, A, B, and C, they're just parameters. They have no operational meaning. And you can use them as you see fit to make sure your predictions don't depend on the cutoff. It's not very many parameters to fix an infinite number of quantities, but that theorem that we just proved tells us that we don't really have to worry about an infinite number of predictions. We only have to worry about the cutoff appearing in precisely 2 settings, namely scattering and propagation. So, you know, you should start to feel a bit confident that one could play this game and win. So I've got to tell you what the game is. Okay, so when you see a Lagrangian written like that, you should start to think of the thing that I've called lambda phys as kind of like a non-interacting Lagrangian, and these three extra terms there is kind of like interactions. They're funny looking interactions, but you should think of them as interactions. And if you want to do a calculation with a theory that has a free part and some interactions, well, you should think of perturbation theory. So these A's, A, B, and C should be small. Why should they be small? Because we know we're more or less on the right answer by putting in the physical mass of our particle and putting in the physical scattering amplitude. We know that we're more or less correct. That's a good model that will match low energy experiments. And there are high energy corrections by coming from these three additional fantasy interactions here. So A, B, and C are called counter terms. And you should think of them as additional interactions. And the whole name of the game, the whole trick, is to determine these things iteratively. There we go. That's how you determine them, iteratively in powers. So if we just look at that Lagrangian and think of it as a Lagrangian and these as interactions, then we can work out its Feynman rules. So yeah, there's some hard work right there. I'm just going to say, so I'm going to write out the Feynman rules to save you the bother. If you think of lambda as being sort of lambda naught phys plus lambda phi 4 phys plus some additional interactions, then you just do the whole Wick's theorem power series thing and you'll end up with diagrams and Feynman rules. But we're going to end up with some additional vertices. We're going to end up with some parts of the diagram which come from the A, B, or C parts, and they depend on A, B, or C. So I'll draw the additional Feynman diagrams in momentum space. Well, here's the old one. We also pick up an old Feynman diagram from the original interaction, but now we get some new interactions. This is the new novel part of the whole story. So we get a new vertex, which I'll draw as kind of a tensor product symbol. It just means another kind of vertex. Don't interpret this as a Feynman diagram. It's a new kind of vertex. And if you go through the machinery that we developed over the past semester and a half, you'll see that that vertex equals 2i a k squared plus b. So in fact, these two terms here kind of collapse together in momentum space. Right, this was, I hope this is, you could have seen this coming. I mean, in momentum space, d mu phi is just multiplication by k mu, k squared in fact. So we have a k squared plus b in momentum space. And that's why we're getting this value a k squared plus b associated with that. So in fact, these two terms kind of collapse together inside the perturbation theory for this new Lagrangian here. And we have one additional degree 4 vertex, and that's 4 factorial times I times C. So we have new free parameters, we have more diagrams, but we have more free parameters. All right, now we're going to use these additional degrees of freedom, A, B, and C, to explicitly cancel out the remaining dependence on the cutoff. Here's the argument. This is like, I'll call it a cartoon BPHZ. This is an absolute caricature of what goes on in proving the BPHZ theorem. That's an extraordinary piece of combinatorics, very hard work. Yeah, there's no getting around the hard work. So we know we've really done some proper science because we ended up with a decent amount of combinatorics at the end here. So we determine A, B, and C iteratively. So this is morally is how it all works. Of course, the details are immense. There's immense numbers of details you have to worry about. But at its heart, what I'm about to write now is how one gets rid of all dependence on the cutoff by shifting parameters. All right, so it's an inductive argument. So, step 1. Suppose we've determined A, B, and C at order lambda p to the n. So we're on the way to getting rid of all the dependence on the cutoff, and we've gotten up to lambda p to the power n. And so far, nothing depends on the cutoff. What do we have to do to determine these quantities to order n plus 1? Well, we want to make sure that the diagram corresponding to the propagator has a mass exactly in the right place, as in it's giving the right propagation, and that the scattering amplitude matches our physical, experimentally determined scattering amplitude. So we determine the values of these parameters at the higher order by requiring the diagram with two legs to have a pole at MP. That's the same as saying that this diagram represents the propagation of a particle with mass MP. Oops. So this diagram is computed at the higher order, obviously, otherwise you wouldn't have anything to do. And it's important that the residue equals 1. Otherwise, we have a renormalized propagation. And we require that the scattering amplitude is I times lambda p minus I. And we're done. That's the recipe. All the other diagrams don't depend on the cutoff. And this determines all the parameters A, B, and C. Now, at this point, you're kind of entitled to not believe me. Oh, yeah, a question?
Here's a question. I'm wondering about the order of lambda pn, because we are also having the other parameters.
We also have the other parameter, that's right, yeah. We have to set that.
We have always like determine ABC at order lambda p. We shouldn't be like lambda p, m, and z.
So we have, where is it gone? C is the lambda for the counter terms. So that's, these powers of 4 are determined by these powers of 4 here. So C is fixed by, so the one parameter that's small and that we're going to expand in is lambda phys. These things here, we're going to use them to cancel off these terms here. So you're wondering why there aren't two small parameters. Is the question that you're wondering why there aren't two small parameters that we're expanding in? Yeah, okay, so the answer is that we only expand in this and we use all the other terms to cancel the divergences. And that's why we organize things in this way like that. Yeah, a question?
Where is the four-leg diagram for this?
The four-leg diagram is the scattering amplitude diagram.
Okay.
So the scattering amplitude diagram, it's this one. And that should be minus I lambda phys, right? Okay, so there's lots of questions that this procedure should leave open to you. And one is like, does it work? Well, one way to do that is to read through the proof of the BPHZ theorem. And then you'll be convinced by the end that it does work, that in fact you can eliminate every divergence that turns up. Another one is just to shut up and calculate, right? So you can go to order lambda p, then you go to order lambda p squared, and you go to order lambda p cubed. And then every time you go to a higher order, you don't find additional divergences, and you find that you can solve for A, B, and C. And after a couple of orders, you'll just give up and accept that it's true. So actually, I think that the second approach is is a much more useful one at this level. I think you'll gain a lot of intuition in just calculating. So you take a process, the scattering amplitude, you expand to order lambda squared, so you know there's going to be a divergence somewhere, and then you just find out how to set C, B, and A so that that dependence on the cutoff goes away. And you'll be able to do it, and then you go to a higher order, and then at some point you'll give up. Now, that's, that's how it all began. Renormalization theory was this calculation recipe that people developed to make sure that their predictions didn't depend on the cutoff, and they saw that it always worked in some cases and it didn't always work in other cases. So I guess I should say one or two words about non-renormalizable theories. So what's a characteristic of a non-renormalizable theory? Well, it's one where you can't shift a finite number of parameters and match and leave all your predictions not depending on the cutoff. Well, so a non-renormalizable theory is not a renormalizable theory, so it's one that requires an infinite number of parameters to ensure that operationally defined quantities don't depend on the cutoff. Now these things exist in proliferation. There's an infinite number of non-renormalizable theories. They're everywhere. I'll just make one comment, is how do they appear in renormalized perturbation theory? This is kind of interesting criteria for what does a non-renormalizable theory look like when you do renormalized perturbation theory. Well, as before, you write lambda equals lambda naught phys plus some interaction plus counter terms. And you might say, okay, I'll try and get away with only a finite number of counter terms. Step one is to calculate stuff to order lambda, whatever lambda is. The theories that we're talking about might have multiple interaction terms. Let's just imagine that they have one that depends on an interaction parameter, lambda p. So you calculate to lambda p, and you need counter terms to eliminate the dependence on the cutoff. How many do you need? Well, a finite number. At a finite order, it's always possible to write down enough counter terms that will eliminate the dependence on KC. That's always possible. The problem is, as you go to higher orders, you need more and more counter terms. That's the signature of a non-renormalizable theory. You can't tell from the outset that you need an infinite number of counter terms, but you can argue that as you go to higher and higher values of this interaction parameter, higher and higher orders of this interaction parameter, that in order to cancel the dependencies on the cutoff, you need more and more counter terms. Now, counter terms correspond to parameters that you need to fix by experiments. So if you need an infinite number of parameters that you need to fit by experiment before your theory can start making predictions, then it's a pretty poor theory. And that's why we don't like them as models. They're very good effective models because they predict stuff at low momento, and those predictions can be fixed by a handful of counter terms. They're just not very useful as ultimate theories of reality because they may be finite. Let's be clear, they are finite. They lead to finite values for all predicted all operational quantities. But you need an infinite number of parameters to determine those quantities. So they're not useful as theories of reality or theories of everything. Now there's quite a few examples of non-renormalizable theories. The most canonical one is gravity. So if you write down linearized gravity, that's a wave equation, comes from a Lagrangian, and you add in an interaction term coming from perturbative corrections, then to the metric, then you will have a theory which has this quartic term in it, and it turns out to be not renormalizable in exactly this sense. You expand to higher and higher orders, and things just don't cancel off. On the contrary, you need more and more counter terms to deal with the dependence on the cutoff. So just taking linearized gravity is not a good renormalizable theory. And so you might say, well, why take linearized gravity? Why not take like proper gravity? Well, that should work, maybe we don't know. It's just very hard to work with that as a theory. I do understand that recently people have written down a linearized supergravity, which is starting to look like, through magical cancellations, that it might be renormalizable. N equals 8 supergravity. I think that's not yet settled. But it's possible that there is a linear gravity theory out there which is renormalizable, but due to extra miracles that happen at order by order, lots of extra cancellations seem to happen at higher orders. All right, that's it for perturbative quantum field theory and renormalization. Everything I've told you, you could apply to any theory that depends on any model that depends on some parameters. Everything I've told you here is sort of transferable skill away from high energy physics. Next lecture, we're going to dive into a class of theories that we haven't met yet, ones that we need for the description of nature, namely gauge theories. They're kind of like bosonic theories, but with lots of what we might call spurious symmetries. They're not physical symmetry. They're not arising from a physical symmetry. They arise from a redundancy in our description. And they are the last sort of piece in the puzzle that we need to describe the forces that we observe in our everyday experiments. Okay, so I'd like to finish that. Thank you very much.